Today's actually an extension or a carry-on from last week's presentation regarding utilizing other tools, other EasyPower tools with the Arc Flash database that's developed during an Arc Flash study. And today we're going to talk specifically about harmonics. So let me see if my poll question, if we could get some feedback. So the first is, do you actually have the EasyPower tools? And appreciate folks participating. So it looks like we have a little bit of a split here. And then the second question is, how frequently do you use them? The ones that do have it. Good, I appreciate that feedback. And so here's what people are reporting here. Okay, so as I indicated last week, we believe that there's an extreme amount, a little bit of a hyperbole, a lot of value in the database that's generated by an Arc Flash study. And to that end, we believe it can be an effective communication vehicle between you and your client base if they understand more about what additional knowledge you have about their system beyond just the Arc Flash. And so this is, like I say, an extension of what that dialogue was last week. And so the issue of harmonics is not a new topic. In fact, it's probably as old as AC electricity, and consequently there's a lot of data on and knowledge on how to analyze a system for harmonics. Basically, anytime we utilize capacitors, because of the heavy inductive loading and the heavy inductive content, there's going to be a potential for resonance in any system. And consequently, harmonics actually are becoming a bigger issue in both in older facilities and newer facilities. Part of this is it's not a matter of if you're going to have a problem. The resonance is really just the only variable in the equation is what frequency the resonance will exist. Now, in older facilities, we seldom saw harmonic frequencies beyond the third, fifth, or seventh harmonic, and so it was relatively simple to create a filter if we needed power factor correction, to create a filter that was detuned or missed these common harmonics. It was just a matter of setting the notch in the resonance, moving that resonance point higher or somewhere in between the primary resonance of the lower frequencies. Today, though, because of the advent of PLCs, VFDs, and motor control systems that use switched power, there's a lot of very high frequency harmonics induced, not just harmonics, just a lot of high frequencies at various points in the spectrum based upon which type of controller we're using. And the sharper the waveform of that switched power, the higher the harmonic content. So we're actually getting a lot of frequencies, and a lot of those frequencies end up being harmonics of the primary frequencies that we're using, whether it's 50 hertz or 60 hertz. And this is probably most noticeable in temporary facilities or older facilities where there was just no thought given to the need for doing frequency or filtering. And in newer installations, when we do changes or make additions to the system, whether it includes capacitors or not, whatever filtering we may have had when the facility was built may no longer be adequate. So the bottom line is it pays to be aware anytime we're making additions to a system. And frankly, it pays to be aware when you first do a model of the electrical system to see if there's any sensitive areas, both physically in the system or frequency-wise in the system, because you can, with a fair amount of insight that the database offers, you can anticipate where there could be some sensitivities. Now, what I'm about to do has really no resemblance to an actual harmonic study. Harmonic study, a full harmonic study, can be very time-consuming because harmonic issues can be erratic and based upon, or change based upon system loading or system configuration. Frequently, you'll find when you have backup systems like standby generators or UPS systems or complicated motor control centers, you can have harmonic issues that can appear some of the time and not appear at others, and consequently it can be very difficult to really pinpoint the actual source. So a full harmonic study involves a fair amount of data collection and then re-simulation with that data and some trial and error based upon the findings, and you need to take into consideration all these factors when you're trying to isolate the harmonic sources. And then the design of a filter system needs to, as I say, accommodate the potential for other system changes or the changing configuration that by adding a filter could change the resonance in a configuration that wasn't having a problem. So a full study is relatively complicated. What I'm going to do here is a real quick overview to do a snapshot of a system that and isolate or potentially focus on areas that could have problems or potentially be problems just based upon the data we collected during our flash study. So it's a starting point. It's a point to have a conversation with the client because he knows or they know where they have harmonic sources, and therein lies the challenge of trying to close this loop. With that, let me jump into the tools, and we're going to use the same example we used last week, or at least we started with, and I don't have more technical problems. We'll jump into this. So last week we took a rather complicated new design that was starting off, that had a lot of large motors at the end of very long impedance runs with a lot of transformers, and we were trying to utilize power flow to anticipate what the power factor correction needed to be. And so one of the questions that came up is, well, what's the cost of the power factor correction compared to the penalties that we may be getting from the utility? I think that's a valid question, and I'm not the person to ask. The other thing that I bring to, or the other question that may be asked is, are there alternatives to deal with the power factor correction, and or by inducing all this capacitance, what have we done to the harmonic sensitivity of the system? So with that said, this is, if you recall, this is our system, and we have a bunch of large motors, and if we just look at the power flow, I'm going to go up and solve my power flow. I want to go to the utility and display our one line, the MVA and power factor. So what we see is with all these motors running, the power factor is below 85% without any type of correction. And these are running about 40% as far as the motor loading. So what we did is we went in and put some power factor correction capacitors, and we want to see what that's done to our harmonic sensitivity or our resonance. And so with each of these dual motor loads, we're putting in a capacitor that's fairly substantial. And if we go into the harmonics analysis, we can scan this bus and see if there's a resonance. So this is a single point. You'll notice we have a whole new set of icons at the top. We have the summation, the bar chart, the scan, single point injection, and all sources. What I'm going to do is pick a particular bus and then scan the frequency to see if there's any sensitivity to any specific frequency. And what we see with a 1 per unit injection, current injection, that there's a fairly significant impedance response at least 2 frequencies. And so this looks like it's about the 10th harmonic, and this over here looks like it's somewhere near the 18th harmonic, which I surmise is by virtue of our, I need to move my controls, by virtue of our capacitors. Verify the capacitors are doing this. What I'm going to do is move this window down, come back to my one line. I'm going to come over here to this bus where I have a capacitor on a switch. We're going to run the same scan, and here you can see I only have one lobe, and it's the lower one. And so now if I close that capacitor switch, yes indeed, the sensitivity or the resonance that I see with some fairly high response at the 10th, in this case it's the 9th harmonic, and just between the 17th and the 18th because of these capacitors. So the bottom line is, when I added all these capacitors to bring down my power factor, I've introduced some resonances. Now, that's not necessarily harmful as long as I don't have frequencies at those points or those resonance points. So now the next question becomes, what if any do I have as far as frequencies at those points? Well, in the current database, because we're using synchronous motors, I have not entered any harmonics. So what I'm going to do, just for grins, is I'm going to say, well, instead of a synchronous motor, what if we go ahead and put in a VFD? We can leave it at a synchronous rate and control these with VFDs. And the way I do that is in database, I come back and say I want to make this a variable adjustable frequency drive. Hasn't changed my motor specs much, but it does permit or make me think about the injection of harmonics from this particular system. The one point to be made here is that the spectrum module will work standalone if I inject a specific, or if I specify a specific fundamental current, or if I'm using power flow where we're calculating fundamental amps, it'll use that to give me a more accurate answer for the current in the system. But what we're going to use is the temporary or typical data from the database. It's in the library from the industrial manufacturer slot. We're going to say this is a pulse width modulated controller with a 42% load, and this will enter typical frequency and harmonic currents for the harmonic content that's predominantly in this type of controller. Now, if your manufacturer's data has specific harmonic content, then that's what you would be using here. You could enter those numbers straight into this spreadsheet. So now that I've got these, I'm going to take a copy of this and put it in these other motors. And make these all harmonic generators. And the point I'm trying to make is that this is not giving me a hard and fast answer. It's giving me a what if, quick and dirty answer, but it has a fair amount of bearing because we are using the database and we are using the manufacturing data or the typical data for that type of system, for that type of motor controller. Okay, so now I've got all my motors set up for AFD, go on the harmonic focus. Let's go back to this switched bus. I'm going to scan the bus now. So I still see the lobes which is we didn't do anything to change the lobes. What I'm most curious about is what sensitivity there is. And the way we check that is the summation of the harmonics that are in the system. And what we see here is that the total harmonic distortion in the voltage range is 9.34%. And I'm going to look at our harmonic options, one line output. So we're looking at the per unit bus voltage. If we want to look at the spectrum of what these variables are, you can see we have heavy content at 5, the 5th harmonic, the 7th harmonic, the 11th, and not so much at the 13th. And this was the area where we see our resonance. So let me go back and make sure see if it changes with my value of the capacitance. So let's put this back in there. So now you can actually see it increase. It seems to me it increases. Not sure that I did that accurately. The capacitors do have an influence on where that resonance is, and I see right here I have a 5th harmonic content and a 7th harmonic. So I guess bottom line is I'd have some serious issues just throwing that much capacitance if I had this type of harmonic content in my system. It also brings back the questions like, well, with the, and this gets a little bit fun, but with the, what happens to my power factor? Do I need all that capacitance now that I'm using the VFDs? So let's go back to power flow, come up here to our utility, if I can find it. Now you can see we've actually overdriven the power factor by having the capacitance in there. So the possibility, if the purpose is to reduce the power factor correction or power factor penalties, a partial solution would be to use VFDs. Bear in mind, though, that we're going to have to deal with the filtering because of the potential resonance. Okay, well, if this ends up being a little bit more convoluted than I wanted to get into, let me go into another example. And this is an example that's in the sample file. They're installed with the tools. And the point I want to make here is essentially the same, and that is if this is the system that I've collected or my database I've generated, there's already some potential for capacitors to be installed in the system, especially when the system has very large motors. And my question is, now that I've done the study, is there a potential to look at or a need to look at what the harmonic condition is? Let's say specifically the customer's asking that we want to convert this large induction motor, what energy would be saved by going to VFDs? And so natural question would be, okay, this much energy could be saved, but are we inducing more harmonics problems? So back in the harmonic spectrum, and the way I would do this this is I'd go into the find. I like to go specifically to any large capacitor. Let's just start with the first one, which just happens to be right here. I'm in the harmonic focus. We're going to look at the frequency response for this particular system. You can see we have a very sharp peak at the fourth harmonic, which I suspect was intentional when they put that capacitor in there. And so at that point, I think we are well advised to do some fairly serious consideration about what harmonic conjunction is going to be done. Because if I take that capacitor out of there, that resonance point goes away and we're down with a very low response. But you get the point. The fact that we put a large capacitor in here, we knew there was going to be a resonance, so we tuned it intentionally at a frequency that the system would never see. But as soon as we're starting to put in a VFD that has any content in that particular range, then we may have to contend with the potential harmonics issues that are going to potentially arise because we have frequencies in that resonance point. Now, then the other part of the equation is what if, and this kind of goes into the need for harmonic study, what if we're having problems that we don't know how to troubleshoot? We have transformers overheating, we have fuses on a specific phase blowing, we don't see any particular irregular currents. So the next place to look when you're kind of out of troubleshooting ideas is harmonics. And at that point, when you're kind of down the road and you're just seeing a bunch of system issues, at that point you are better off suggesting a harmonic study be done, and by using at a first pass, just as I'm doing here, looking at in this case, the high value capacitors, those would be the places we'd start off looking at taking data log measurements for harmonic content and power quality measurements. Okay, so did we do any good? The point I'm trying to make is that there's value in the database that was collected when we were doing the ARC study, and the more accurate that system is, the accuracy of the system can actually be developed utilizing power flow by taking regular readings, and this I would encourage your customer to do themselves, to take regular voltage and current readings at specific times on a periodic basis and compare those with what the power flow projections are for each bus. The adjustments that could be made would be the loading, the motor loading, and potentially any impedance changes that we have upstream that would affect those voltage and current readings. And as we get those elements dialed into the model, now the model becomes even more valuable in terms of predicting failure or anticipating locations of issues when we go to make a change, specifically trying to lower the power factor correction costs or lowering the energy consumption of a plant by using some sort of a digital controlled motor. Okay, so that's, I guess that's the bottom line of where I was trying to go with all this. And let me see if there's anything else. I do want to mention that one of the areas that we stand squarely behind you as a consultant using the EasyPower tools is the ability to step in and help you with technical expertise if it's an area that you may have questions or would like some additional training or assistance in doing modeling or analysis. So, and this is something that can be done with without necessarily, if you will, interfering with your relationship with your customer. likewise, anybody that has questions specifically in modeling harmonics, notch filter design, or utilizing power flow for dynamic stability, I'd encourage you to consider attending the regional training that will be coming up here end of next month in Portland, and that, I think that improved knowledge and understanding of how to apply the tools could help your value proposition with your client base. I appreciate everyone for attending today. By all means, I encourage you to visit EasyPower.com and look at some of our webinars from the Thursday webinar. These are the ones that are most in-depth technically,